Hello, everyone. This is Carolyn Chapel, and I'm going to be talking today or just giving an introduction to continuous random variables. And we've already talked about discrete random variables. And when we had discrete random variables, we could, list our possible x's and then the probabilities for each. Sometimes their x's were infinite, and we did have formulas for them in the case of the Poisson, or we had quite a few, but in the continuous system, we can't even do that because continuous random variables have a continual interval of some sort as outcomes. So for example, a person's weight, which could range anywhere from 0 up to 2 ton or more, I don't know. But so what we have to do is find a different way to represent their probabilities. And we do so using a probability density function. Or sometimes referred to as a PDF, probability density function. And what it is an equation used to compute probabilities. Of a continuous random variable. And we're just going to look at a few of them in this course. These random variables do satisfy just a couple of situations. First of all, if you were to graph this function, the total area under the graph of the equation will, over all possibilities of x, whatever that random variable happens to represent, possible values. Must equal 1. This is similar to adding up all of our probabilities and getting the number 1. If we're talking about a continuous random variable, we talk about areas under our curves. And the second one is that the height of the graph, excuse me, must always be greater than 0. Greater than or equal to. For again, all the possible random values of the random variable. So similarly, we would need the total area to be 1, kind of like adding all of our pieces, and our curve has to be always above 0 for values that this random variable takes on. When we talk about a random variable, also, we will not be looking at for the value, the probability of x being a single value. Because if we're talking about a continuous situation, we have so many outcomes. So for even in the example, if we go from 0 to 1, and that was our possible outcomes, there are so many outcomes in that small interval that the probability of it being a single value is going to be 0. So what we will look for in continuous situations is we're going to be looking for the probability that x is in an interval of some sort, either between two numbers, smaller than some number, or larger than another number. Okay, let's talk about this. What I'm going to do is we're going to look at, first of all, our uniform, and then we'll branch out a little bit from that. So I want to remind us that a uniform distribution is one that's flat. Okay, it kind of looks like, let's just say our X value takes on, from 0 to, let's say, 30. So if it takes on all of those values, our uniform situation would look something like that, basically straight and flat. Now, for it to be a continuous distribution, we have to remember that the total area under this curve has to be 1. So if this were going to be equal to 1, that area under that curve, first of all, it's the shape of a rectangle whose base is 30. That means its height is also 1/30th, because the area of a rectangle is length times width. We will be looking for values or the probabilities. Let's just do an example that X is between 7 and 19. Okay, what we will do to find that probability, this probability will be area under that curve over that interval. So that's how we find probabilities in a continuous situation. We will be looking for the area from 7 to 19. Now notice the area from, if I include 7 or if I include 19, that is negligible because the area or the probability of it being an exact value is basically 0. So whether or not we have inequalities with the equals or strict inequalities is not going to change our situation whatsoever. So for something like the uniform, we have that is going to be the area in that region. That's how we find probabilities. Area under curves equals our probability. So in the uniform situation, it's a rectangle. And the rectangle, we have its height, which is 1/30. And its base is that distance from 7 to 19, which happens to be 12. So the probability that we do get the value between 7 and 19 is 12/30, or 2/5, or we could turn it into a decimal. We could write it as a fraction like I did here. We could turn it into a percent. I could also do another one, X being greater than 27. Okay. And I will use a different color for that. So we have some different pieces. So let's say 27. Now notice that our curve outside of here is 0. So basically we have this rectangle here, and then we have nothing because X cannot take on any values outside of the 30. So kind of remind ourselves that there's going to be a lot of places where our probability is 0. So for example, rolling a die, getting it to be an 8. That's not going to happen because our numbers are 1 through 6. So getting bigger than 30 in this particular uniform is 0. So again, to find that probability, it's the area of that little rectangle. So the height times our base. And I'm going to reduce right away. So we get 1/10. Okay. We use the uniform just kind of as an introduction, but one of the biggest curves that we work with is the normal curve. And I'm just going to introduce it in this video, and we will dive into it a little bit more in some of my other videos. The normal curve, or sometimes referred to as the bell curve, and we have talked a little bit about this in previous chapters, and it is like a bell. Draw my little bell. I could give you the formula for this, I will. If you want to know what that curve, the equation of this curve, it is, and it's ugly, so just kind of bear with me. Get this ugly fraction, we get 1 over the standard deviation, so sigma, times the square root of 2 pi. And then we have e, we have a really ugly exponent in there, 1/2. And then we have inside here, x minus our mean, all over our standard deviation, and all of that is squared. So where this is x, and y tells us how high we are. Okay, you will never use that equation. We will use, it is used though to get all the technology that we use to evaluate things. But in most courses, we just learn how to use the technology that is based on that formula. Some things to kind of remember, in your normal curve, the center of that normal curve is our mean, or mu. We also have what we call inflection points. And an inflection point is a place that where it turns kind of like from being a bowl down to being a bowl up. So you can kind of see it's curved down to being curved up. That is sometimes referred to as an inflection point. This kind of helps us draw the shape. And in our normal curve, these happen at mu plus 1 of our sigmas and mu minus 1 of our sigmas. Okay. I also want to remind us of some other things that we had in this region. We learned it about how spread out our data is, and that empirical rule, we realized that there's roughly 68% of our data in between those two inflection points. So if you can remember that empirical rule, that 68, 95, 99.7 rule, the 68% is when we were within 1 standard deviation. I'm going to put mu plus or minus 1 standard deviation gave us that 68%. We would get 95% if we went 2 standard deviations. If we went up another one up here and down another one, we'd pick up more of our data. And we'd get 99.7% of our data if we go 3 standard deviations in either direction. Sorry, that's kind of a funky little sigma there. Okay. I'm going to draw a few pictures about what happens to our curve as the mean changes or as that standard deviation changes. You can kind of just see some rough pictures. Again, we're just going to do a brief introduction here. So let's say what happens when our mean changes. Okay, so here's our wonderful x-axis, whatever it happens to be. And let's say that we had a mean of 5. So mu equal to 5. So if this is a normal curve, that means the high point, that top of the bell, is going to happen at 5. Whoops, and I missed. Okay, so they'll put our 5 right there. If our mean changed to say 15, that just is going to shift this curve up. So we'd have the same curve, but we'd have it up here. Instead of at 5, it'd be centered around 15. Okay, so all the changes in the mean just moves the curve up and down the axis. The curve always is symmetric. It is nice and even, tails off rather quickly towards that axis, does not go into the negatives whatsoever, always stays completely above. What happens when it changes in our standard deviation? I want to remind you, standard deviation is what we use to represent how spread out your data is. So let's just say we have, here's our mean. I don't know what it is. You can label it if you want to. And let's just say, for argument's sake, I don't know for sure, that this is equal to 2. Okay. So I don't know how exactly steep or combined it would be, but let's say that we're going to increase this to 4. So let's draw in a different color here. To equal to 4. Now that means it's a larger standard deviation, which means our data is more spread out. And we're going to have to go further. So if I were going here to 2 above, 2 below, we'd see those inflection points. I'm going to have to go 2 out and 2 below, 4 above and 4 below this time to get those inflection points. What's going to happen, I like to think of it as if someone stepped on this top and pushed everybody out. Because remember, we have an area of 1 in here. We've got to keep the same area. So thinking of this as numbers of people underneath there, 100% of our data is underneath this curve. We're going to have to spread them out. So we're going to put some of these guys are going to come down here a little bit more. So it's going to come here a little bit more, maybe come up. I don't know. This might be a bad way of putting it. So it's kind of a little bit more spread out. It does still continue to come down towards 0. It probably comes down a little further out. These are very difficult for me to draw, but I just kind of trying to get you to get the feeling. So if you increase your standard deviation, you're going to kind of push on here and force those people elsewhere. Similarly, if we had made a smaller standard deviation, so we're going to push them together and squeeze them together. So we're going to actually get this thing to be a little steeper. Oops. And so forth. Still going to have that bell shape. Still going to have all of our people in there. It's going to be less spread out. So our 100 people are going to have to be stacked inside of each other a little bit closer together. All right. Okay. One last thing before I end this video, and that is just going to lead into my next video, which is going to be on our standard normal curve. So in general, we have a normal curve, has some mean equal to mu and some standard deviation. I'm going to abbreviate this, equal to that symbol. And then it will look nice bell curve. Okay, so there's the mean. And again, if I go up 1 standard deviation and I go down 1 standard deviation, we get, again, empirical rule says roughly 68% of our data in that region. What we do with this is we use technology to kind of help us out. But before we had all the technology, we used tables. And we would transfer this to what we call the standard normal. Okay, it is still a normal curve, but we wanted it to be nice. So what we did, and it is, I like to think of it as a man-made curve, but it is a normal curve, but we wanted it to be nice and centered, and we centered it around 0. Okay, so we have our mean of our standard normal equal to 0. And we wanted us to have a nice standard deviation. So we let it be 1. So our mean is 0, standard deviation is 1, which means if I'm between 1 and -1, we're going to get 68% of our data. If I'm between -2 and 2, I'll get 95. If I get between -3 and 3, we will have 99.7. And what we do is there's a little formula that I believe you've already seen that'll take us from this point curve, any general normal curve, and put it into the standard form by calculating what we call our z-scores. And our z-score is taking our data value, whatever it happens to be, subtract off our mean, and put in, divide by our standard deviation. And that will take any normal curve and standardize it, so to speak, and put it into that standard normal curve. Okay, the next video that I do create will be just about this standard normal curve, a little bit about it, how to use it, using tables and possibly StatCrunch, but I believe I'll save StatCrunch for when we're dealing with just the regular one. But I will show you how to use a table in order to calculate this areas in between pieces. I already know that if I'm between -1 and 1, I get roughly 68%, -2 and 2, roughly 95%, between -3 and 3, roughly 99.7%. Again, I apologize for the tickles in my throat as I was coughing through this video, but it is that time of the year with allergies. Again, this is just an introduction to a continuous curve, which means the variable can take on any value that it wants to. Now, the probability of getting these values way up here and way down here is very, very small, very unlikely. So it does come down a little faster than my pictures tend to show, but we will talk about those in the future.